I'm Emma, and thanks so much for coming. I'm from Armenia, and I'm here today to talk about property-based testing the Python way. How many of you write tests? How many of you know about property-based testing? How many of you have done it the Python way? So my talk is an introduction to a new method of testing called property-based testing. And for you not only to understand what it is, but also why it matters, I'll go over both the traditional and property-based testing approaches with a focus on hypothesis. I'll describe the problem which we're going to approach from two different testing perspectives. I'll explain what property-based testing is and why it matters. I'll introduce hypothesis and why choose it as a go-to property-based testing tool. Then I'll talk about the differences between the PyTest parameterized and hypothesis approaches. I'll compare these two. And finally, I'll talk about advantages and disadvantages of both. So the problem that we have is the following. In Hog, the player rolls 2 dice, and we have 2-sided dice. The score for the turn is the sum of dice outcomes. And if any of the dice outcomes is a 1, the player's score for the turn is 1. So let's have a look at the snapshot from the demo of the solution of this game. As you can see, we're rolling 2 dice, and when we're getting 4 and 2, the total for the turn is 6. And there are other cases. This is how the game works. And so now, if we want to test this function from the traditional testing perspective, it is going to look like this. This is an example-based test, and this is how an example-based test looks like in its cleanest and most abstracted version, using PyTest parameterized. So we have just one test function, and we're passing 2 arguments to it, input and expected, which is the expected output. We have assertions in our test function. And in the decorator, in the parameterized decorator, we have input expected. We have this pair as the first argument, and we have a series of input-output like pairs. And as the second argument, we have a list of input-output pairs. In this case, we have 3 test cases in our decorator. And parameterize is a smart technique because it allows us to test like our function in just one single function. For example, here we have 3 tests in one function. And when this test is executed, PyTest actually automatically turns this into 3 separate tests. So it does that process for us automatically. And when this test is executed, we see that 3 tests passed. So actually this worked, but it's still pretty complicated. Do we really want to write all of this code and spend lots of time writing this? For example, with parameterize, we came up with examples. Here, these are examples, these test cases. And we produced the data that our function executed against. But what about some important and interesting edge cases? Do we want to write code that's difficult to debug? So what if I told you that you could write simpler code and get better result? That is the main motivation behind property-based testing. So property-based testing is a method of testing where tests are written to assert that our software satisfies a set of properties instead of outputs, instead of exact and specific outputs, for many different inputs instead of specific fixed input. Property-based testing kind of generalizes an example-based testing to test the software for any valid input instead of specific examples. And it also focuses more thoroughly on the behavior of the software because in parameterized case, it's not that thorough, it's not that precise because we're drawing conclusions from very specific examples. But in this case, we're focusing on the behavior of the software by testing general properties of it instead of just testing our own expectations of how things should work and how we tested our expectations of how our functions should work. And so by testing general properties of our software, we're describing its behavior more thoroughly and more precisely. And why property-based testing matters? Because it matters because it allows us to focus on what is very relevant to our test. In the property-based approach, we are forced to think about our input in a more general way instead of coming up with examples. And we're forced to also think about what kinds of properties our software has. And in our tests, in property tests, we're explicitly specifying our assumptions, and we're then checking for their truthfulness. This approach is very effective because it allows us to catch some bugs that might go undetected with example-based testing. And how do we do this? We do this with the library called Hypothesis. You can install it with pip install Hypothesis and run these tests written in Hypothesis with PyTest. From Hypothesis, we're going to import given, which is a decorator-like parameterizing example-based test. We're also going to import strategies, and a strategy is a generator of data, which is going to be used to generate hundreds of random inputs to our function. Properties, what are properties? They are the outputs in these property-based tests. They are general claims about our software's behavior. They are the things that are going to specify our assumptions, explicitly specify in our tests, and they're the things that are going to assert that our code is correct. So we want to check and test for their truthfulness. So this is the example with a hypothesis, the property test for our function. So from hypothesis, we import given and strategies, and we have the decorator given, and given is going to describe which type of data we want our function to try, and in our case, we want to try a list of integers, and we're going to generate this data, list of integers, with strategies. So we're going to call lists from strategies and integers. So this decorator knows how to understands what kind of data we want to generate, and strategies are going to generate that hundreds of input data, and they are going to try our logic, which is in the test function, many times. We can also specify more details in this decorator. For example, you can specify the minimum and maximum values. You can put also other details in it. But in this case, our test is going to generate this data many times. And during each run, it's going to check for a different input value in a randomly generated range, and it is going to store this value in a database. So this is the general idea about how every property test works. And when this test is executed, we get an assertion error, and this is telling us that Our test failed, and it found an important edge case. Hypothesis found an important edge case, which is the case 1.1, and it tells us that we need to fix our code, that there is a bug in our code and we need to fix it. And this error is stored in a database, and if we don't fix it and we run this code again, it will give the same error, and it will give it repeatedly give the same error until we fix it. And in the parameterized approach, for example, our test passed, yes, but we missed covering this important edge case. But here, debugging becomes easier because it's stored and the error is stored and is reproducible, and this code is also repeatable, and we're able to debug our code. Because the error will stay there and the bug will stay there until we fix it. So why choose a hypothesis? You can do property-based testing without it as well, but hypothesis is a very powerful tool for locating edge cases and also discovering faulty assumptions in your code. Hypothesis has strategies. It's one of the main things about it that makes it a very powerful tool. We generated a list of integers, but hypothesis has strategies for many types. You can also create your own strategies, and you can combine strategies. You can also use the core strategies that it has. And these strategies come with the library when you install it. Hypothesis has a great documentation which provides useful techniques and design patterns. It's easy to design these tests because of all of this. It's easy to debug. It has a randomized nature because it generates random data. This process is randomized, but it's also predictable because of the failing examples that it gives. It's repeatable, and that makes debugging easier. It's robust at finding edge cases, which makes it very powerful in terms of giving us an idea about the behavior of our software, and this robustness is what makes it a very powerful tool. So hypothesis has a very rich functionality. Except strategies, it has settings that you can use to control how the input is generated. Even though it's random, you can disable and enable settings that you can use to have some control over how the input is being generated. If you're doing that in production, that might be very helpful for you. You can look into special functions that also can show you, for example, not just the random input, but also what specific input it generated. It also can show some statistics that you can have more insight into the input, how it generates the input that you want. So I highly recommend you to explore all the functionality that it has in greater detail by reading through the documentation. And I want to go over the key differences between the two approaches. In parameterized approach, we had a long and complicated code. We had many details, and we could do that in hypothesis with less code and achieve better result. In parameterized, we wrote the example data. We produced the example data by coming up with examples. We produced the input data to test our own expectations of how the function should work. But in hypothesis, we generated the input data using strategies, and that helped us catch bugs and discover some faulty assumptions in our code. In parameterized approach, we miss covering an important edge case, and it's very typical to parameterized approach to forget about interesting and important edge cases because it all depends on us. But in hypothesis approach, we discovered a bug in the code when we executed our function, our test. It told us that there is a bug and that we need to fix it. And so hypothesis made debugging a lot easier. So as parameterized approach, property-based approach has some downsides as well. The main advantage is automation. We're actually automating the testing process, and we want to do that because it helps us to think more creatively, and it helps us think about the behavior of our software more thoroughly. And by automating, we're not writing every single example, we're not coming up with examples, we're generating data, and we're just writing some properties, and we're describing our software's behavior with properties to assert that our assumptions are correct. This automation is one of its advantages. The second one is the domain space. In parameterize, we come up with examples, and that process is very limited. We can have a very long list, but that doesn't make our code better. And in property-based approach, we are automatically covering more domain space by generating data. And when we have a big range of input data, it helps us catch bugs more easily than in parameterized approach. It's reproducible. We saw that we reproduced the failing examples, and because it's reproducible, you can share that, for example, with others. You can also use that to debug your code. It's more thorough. It's more thorough about the behavior of the software than the parameterized one. The disadvantages are that, first of all, it's difficult to write. It's easier to come up with examples. It's more difficult to actually come up with properties. It's pretty fast, actually. Hypothesis is pretty fast, but if you have a complicated code in production, it can be very slow to run. Mostly, mainly in situations where you can turn examples into properties. Property-based approach is the best choice, that happens when you have mathematical code, for example, or you have a simple code. But there are situations where property-based approach and even hypothesis doesn't make sense, and property-based approach shouldn't be used. It shouldn't replace unit tests. That's the takeaway. It should complement example-based tests. You should always have both in your projects, and you shouldn't replace unit tests with property-based tests. Property-based tests, like example-based tests, can be substituted with property-based tests when it's easy to turn them into properties. Because in that case you will achieve better results. But if you substitute all of it with property-based approach, it's going to even complicate your code. So the takeaway is that they should complement each other, and in that case you will have better code and achieve better results. Thank you. I welcome questions.
Thank you, Dhamma. So, got the questions. On slide, I cannot see any. Some. Maybe Mike. So this
sounds a lot like fuzzing.
Sorry?
It sounds a lot like fuzzing, except that the input is not completely random, but based on some algorithmic approach with some randomness. Can you compare this to normal fuzzing strategies, and can you clarify if hypothesis uses target-based feedback to generate examples?
I didn't get your question. Can you?
The microphone seems off.
Yeah. I can do SOS.
Yeah.
It sounds a lot like fuzzing, because in fuzzing you have you feed data externally and you generate it on the fly, right? And except that here this data is not completely random; it's structured in some based on some rules. But there's also a randomness component. So. Can you compare it to normal fuzzing strategies? And can you clarify if hypothesis uses coverage-based feedback to drive the samples?
I'm not familiar with that method. If that's a testing method.
Is it part of the PyTest or is it a third-party library like Figma or is fuzzy?
I think it's just a general.
It's a separate entity, I think. A data generator of sorts.
So I'm not familiar with that. Sorry, I can't say. But hypothesis using strategies, it randomly generates the data, but you can also control it somehow, and you have that control over it, and it does it randomly, and that's all.
So I think it's a concept from compiled languages, where you feed inputs and you instrument the code to tell you which code paths were taken, and then you use this feedback to make the generation of samples efficient in the sense that you cover more code paths. Because without that, you can generate 100 million samples and only go for a few lines of code because you just don't have some very special property of the input data that is individual classes, some objects in the function. And if hypothesis doesn't do coverage-based feedback, then probably, many of the samples are not going far.
Oh, okay, so hypothesis repeatedly generates this data, but I say the feedback is the failing. For example, when it gives a failing example and it's stored, you can you know that there is a bug in your code, and you fix it, and you do that not just locally. It's not stored just in a local database, but you can do that on CI tool. And also, as I said, you have some control over it. You can use some special functions. It has some special functions that they can show, for example, at what point what kind of input it generated. So with strategies, you describe the input, but that randomness has some predictability, and it has some things that you can use, like some statistics and other things that you can use to control how that input is generated.
Okay. I have a few more questions from Slido. So the question is, how advanced can a strategy get? What's the difference between something like fakers or fake and random data?
So strategies, yeah. So strategies, it has advanced strategies as well. It's not just the core strategies, but as I said, you can combine strategies, you can customize, modify them, you can create your own strategies, and it can get very advanced. Also, you can create very complicated properties as well, but the idea of property-based approach isn't to complicate and use advanced, very complicated properties and strategies, but to actually simplify the code. But it has many strategies for many input types and for different kinds of data that you want to generate. And the random data is, the process is random because you're not specifying what type of like data you wanted to generate. You describe what kind of data, but you don't specify the exact input. And that's why it's random, the data generation. The difference between the fake, I'm not sure what you mean by fake.
Is Faker Python library?
Oh,
generating
okay.
data? Or like, does it use Faker as well? Like you have names, something like this. Is there?
I don't. No, I think no. It works at the engine level. It works differently. The given works differently, and strategies work differently. But the data is random. Generation is random.
I guess I'm not entirely sure, but the hypothesis focuses on edge cases more,
Yes.
on extreme cases. So, for example, the faker can generate random data, but hypothesis would generate, for example, if you are interested in testing integers, hypothesis would generate like very, very big numbers. And when you are just generating randomly, you will have a 5, 10. So hypothesis more focus on edge cases than normal faker and similar libraries.
Okay, so we are overrunning, so maybe last question. How slow it is? Is it good for TDD to run as unit test?
Hypothesis is pretty fast, but it's as I said, it should be combined with unit tests. In production, it can get very slow when you have a very complicated code. For example, when you have some like neural networks and that type of like complicated code, when you have complicated computations going on, hypothesis in that cases can be very slow, but in general it's pretty fast. So you can integrate and combine it with unit tests and run with PyTest, and it's pretty fast.
Thank you, Emma, very much.
Thank you.